Hi folks, sorry for the slightly late start, just having a few technical issues, which I'm just sorting out now, and we'll get going. Just let me find the screen for you. Hi there folks. Right, hopefully, there we go, got the right screen up. Hi Ultimate again, hi Evan, hi Liz, hi Lily. Right. Okay, sorry to have kept you. Let's have a look then. We're starting today with current voltage and resistance. There are going to be two sessions from me today. Firstly, this tutoring session and then a drop-in session coming up next. Hi, the boss. So just by way of introduction, if you've not joined me before, let me just go through who I am again. Let me just check that I am coming across. Let's just see if my face is on. Let's work. There we go. Hopefully I'm now appearing in the corner of your screen. So my name's David. I'm a physics teacher. I've been teaching for many, many years in secondary and also A level. And I am providing the physics tuition for GCSE for Snap Revise. So we are offering GCSE tutoring. So if you'd like to go to the Snap Revise website and have a look, hopefully I'll have time at the end of this session to share the website screen with you so you can see where you need to go to look at the tuition services that Snap Revise offer. There'll be more than 3 classes a week. We cover the full curriculum. You get quality handouts and access to all the past recordings, and also one-to-one support and drop-in sessions. You can have a free trial of this as well. So just for those of you who've been on before, hi Vikram, hi Dana. You will know from the last couple of weeks that we've been running a competition to win the academic year's membership for the Snap Revise tutoring service. Now that draw has now taken place, so 10 lucky people will have been notified now that they've been awarded that. So hopefully some of you there are winners. I hope so. But 10 people have been selected for those free accounts. Even so, you can still have access for a couple of weeks free trial. I'm not sure, Ultimate, whether it asks for bank details or not, so you'll have to click through and have a look at that. If you want to have a look and get a free trial, then use the code tutor14 at the checkout, and you can have access to the next, I think it's 2 weeks, couple of weeks of tuition and drop-in sessions. And yeah, the winners have already been notified, so rather than announced. So you will have received an email. Please check your spam accounts and things like that if you did enter, just in case an email from Snap Revise has been lost and you've not noticed that you've received it, because it would be a shame to miss out. Okay, thank you for confirming. Our colleague Des just confirming it's a 2-week free trial that you will get. All right, so today we're going to be looking at current voltage and resistance. And hi Anna, I did, and it's correct, Hannah. I did pop a message in the chat just after I finished streaming last time, but I suspect it already left. But yeah, it is correct, and they are the right units, just the right definition. Okay, so we're going to be defining the terms charge and current, and hopefully you'll be able to fully understand how a current forms in a conductor. You should understand that a potential difference is required for a current to flow in a circuit, and you should be able to use the relationship between current, potential difference, and resistance to do calculations and solve problems. So things I won't be covering are what different types of resistor exist and other circuit components, and also I won't be looking at circuit rules. Okay. So the specification points are fairly similar for the boards. We cover all boards. Just to remind you, we don't cover content for international GCSE. It's a bit different, but all UK boards we cover the content for. I won't, so these are all rather small text. If you want to have a look at these in detail, you can download the PowerPoint and you can have a closer look. Suffice to say, the things we're covering are obviously common to all of the boards. So AQA, Edexcel and OCR. And let's move on to the content. So what do we already know? So in the chat, if somebody would like to, or many of you would like to tell me what you know about protons and electrons so far. So maybe start with the proton. This over here is a proton. What are the things we know about protons? Today we're doing current, resistance, and potential difference. Protons have a positive charge. Excellent. First thing. Good. What else can we say about a proton? Thank you, Arav. Arav, brilliant. So the proton's mass, it's a relative mass of 1, whereas an electron's mass is about 1/2000th of an atomic mass unit. Brilliant. You find them in the nuclei of atoms. Excellent. Yeah. And then we've got people now talking about the electron. Good. Electrons are negatively charged. Protons are found in the nucleus, positive charge. Okay, so the proton has a relatively large mass. It's quite a big component of an atom. So large mass, it's +1 relative atomic mass. And the electron has a negative charge. It's a little negative sign there. It's physically a lot smaller. And we've already had a comment in the chat there that the mass of the electron is about 1/2000th of the mass of a proton. So electrons are really, really tiny, basically. They're minute, very small mass, negative charge. What can we say about the charge? So a proton is positive and an electron is negative. So we've got plus and minus. What about the size of those charges? Can we remember how big the charge is for each of them? I think Vikram has perhaps already answered my question there. And he's come back again. Thank you. Okay, so yeah, +1 would be the relative charge of a proton, -1 would be the relative charge of an electron. So what's going to happen between these two particles if they get close to each other? What's going to happen if you bring a proton near to an electron? Yep, thanks, Dana. Thanks, Ultimate. Evan, brilliant. So we're going to get a force of attraction if we bring these close together. They're going to attract each other. Opposites attract, general rule for magnetism and charge. We get an attractive force. What if we put another electron near to that electron there? What's going to happen there? Evan, I don't want to get into exchange particles here due to the force of attraction or giving rise to it. We'll just stick to the curriculum content and keep it at GCSE level. Thanks, Dana. So yeah, the electrons here, if we put them near each other, they're going to repel each other. And similarly, if I put a positive proton there, I'm sure you're going to be very quick to say that they're going to also repel each other. Thank you. Well, same charges will repel. Thanks, Rav. Good. So electrons are tiny. They have the same but opposite charge to a proton. Protons are much bigger. And like charges will repel, opposite charges will attract. Okay, I think we've covered some basics there pretty thoroughly. So current and charge. Oh, thanks, Callie. 1 RAM, I was just referring to the relative atomic mass. I should really call it atomic mass unit, sorry. So the relative mass of a proton is 1, it's 1 mass unit, but it's you don't need to worry about that for the electrical side, the current, voltage and resistance content. Okay, so an electrical current. So what is an electrical current? We talked about protons and electrons. We now need to decide exactly what is an electrical current. So Evan has given a good answer, flow of electrons. So it could be the flow of electrons. Does it have to be electrons though? Thank you, Dana. Ultimate, I see you. Again, all flow of electrons. You're not wrong, but S there. SXX has just said rate of flow of charge. That's actually a definition of current, but you've got the idea that it's a flow of charge, and Evan has 2 now. Thank you. And Lily said charge per second. So you're jumping ahead there. You're defining it perfectly. So an electric current is a flow of charge. So any charge that is moving makes an electric current. So yeah, ultimately, it could be charged particles, could be ions. It's often electrons, and current, I will just add it because it's absolutely correct, is equal to the rate of flow. And we measure current in amps. So the definition of current, it's a rate of flow of charge. And ions, yeah. So if you have a solution of dissociated ions, to just do a little bit of chemistry, so you put a teaspoon of salt in some water, dissolve that salt, you can pass a current through that salt solution because you've got the chloride and the sodium ions having a charge, and they can move, and they will therefore carry a current if they're moving. Anything charged moving is a current. So in a metallic conductor, if we talk about metals rather than salt solutions, what are the things that are carrying the current in a metallic conductor? So something made of metal. Can we have moving ions in a metal? You might have them wiggling around a bit, but generally not flowing. So Evan there, in a metallic conductor, each atom gives up its valence electrons to make a sea of delocalized electrons that can flow. Very precise, detailed answer there, yeah. Free moving electrons. So in a metallic conductor, the current is due to free moving electrons or free flowing electrons. Okay, and those electrons are the charges moving to cause the current. And yeah, a metal has a sea of delocalized electrons, which are free to be influenced by an electric field, which we'll talk about in a moment. So moving to the diagram at the bottom, here we've got a substance here, which is representing a metal. This diagram represents a metal. So the metal has in there a lot of fixed ions. So these are the metal ions, and these are fixed, okay? The metal ions, they can't move around. In solid metal, they're going to stay put. But we have this sea of delocalized electrons out in the metal which are able to move. So if we put some kind of force on those electrons, we're going to make them move in a particular direction. So those electrons here are traveling from left to right. There's the direction of the electron flow. These little negative things. There are free electrons. Sort of red dots with a minus sign on them. So the electron flow is going from left to right. Some of you might remember from your lessons that there's slightly different when we talk about current. Which direction do we talk about the current going in? If the electrons are flowing left to right, which direction is the electrical current going? So the electrons are going left to right. It might seem sensible to say that the current is flowing from left to right in this little piece of metal that we've got in the picture. But actually, current would be described as going from right to left. Thank you, Ultima. So the current is described as going in the opposite direction to the flow of electrons. And that's conventional current. That's what we describe as current when we're describing it in a circuit or drawing it on a circuit. So the electrons actually go from negative to positive, Lily. So they will travel from the negative terminal of an EMF source like a battery or a power supply. They'll leave the negative terminal, travel through the circuit, eventually reaching the positive terminal. And someone's already said they actually move quite slowly. But the thing is about the electrons is that they all start to move at exactly the same time you turn on the circuit. So that's why you don't have to wait for the electrons from your light switch to get to your light before your light comes on. So you don't need to worry about the speed of the electrons at the moment. We're just talking about the direction of flow and the direction of current. So they go from negative to positive. Okay, it's not to be confused with diffusion or osmosis, although we are talking about particles here. We're talking about a process that is driven, and we'll talk about that in a minute. We're going to make these electrons flow by putting a potential difference across the conductor. So we've covered what electrons are. We talked about electron flow in a conductor and how the current is actually in the opposite direction to the flow of the electrons. Okay, so we weren't going to discuss individual components today, but yes, diodes do prevent current from going in a particular direction. So the charge transferred by a current. So current is caused by moving charge. So charge gets transferred from one place to another. And somebody has already said that current is a rate of flow of charge. So current in amps, there we go, current symbol I, unit capital A, is equal to the charge, which we normally use the symbol Q for, and its unit is coulombs, divided by the time, that it takes for those coulombs to move in seconds. So it's a rate of transfer of charge, I equals Q over T. So the charge transferred, sorry, there's an error there, that should be an R. The charge transferred by a current is equal to Q. What can we say that's equal to? Rearranging the formula I've just given you, I equals Q over T. What does Q equal then? What's the charge transferred by a current? I'll come back to cells in a bit, Lily, because there'll be some examples of circuits that I can use to answer that question. Okay, thank you. So Dana says, and Essex says IT, and Evan as well, I times T, brilliant. So Q is current times time. Just rearranging the formula there, which defines what current is. So that's equal to current I over time T. Okay, so Q equals IT. Oh, I'm sorry, I've just drawn I over T instead of I times T, my mistake. IT, there we go. So current times time, IT, Q equals IT. Brilliant. Okay, so we can now use this to make a calculation. Calculate the electric current, which will transfer 15 coulombs of charge in 20 seconds. So we're going to start with the formula we've just defined here, Q equals IT, and we want to find the current I. So the first thing we need to do is to put it back into another form. People have already got the answer there already. They'll calculate the answer. You are correct. No, it's only on a text chat, Donna. Just make sure when you do write the unit for current that you always use a capital A. So Q equals IT. We want to find the current, so I is going to be equal to Q over T, charge over time, which is 15 over 20 in this case, which is 0.75 amps. Absolutely correct, all of those who've popped that into the chat. Thank you. Good. Okay, if we can just keep the chat to context of what we're doing, that'd be brilliant. Thanks a lot. So let's move on to some other examples then, charge current examples. So calculate the time that a 35 amp current must flow to transfer 6 kilocoulombs of charge. So we've got current and we've got charge, and we want to find the time. So we know we're going to use Q equals IT again. And we want to find time. So what's the formula we need to use for this? How are we going to rearrange Q equals IT for this one? So we start with Q equals IT. We want to find the time. So we make time the subject of our formula. What's that going to be equal to? Okay, C has got there first. And D just got them the wrong way around there. So yeah, it's going to be Q over I. So we want to find T. So we divide both sides of this formula by I. That gets rid of the I on one side and it gives us Q over I here. Q over I. Current divided by time. Okay, and yeah, we'll come to the numbers in just a moment. Got to be really careful when you're reading questions in exams, particularly because there's a little kilo in front of the Coulomb symbol there, which means, of course, times 1,000. So when we do the calculation, the time is going to be equal to 6,000 coulombs divided by the current, which is 35 amps. So 6,000 coulombs divided by 35 amps. And that gives you an answer of, I don't know if anyone's got a calculator out and has had a go at doing that, 6,000 over 35. Answer in seconds for the time it takes for that charge to flow. You should, I'm not going to expect you all to get a calculator out now, but you should get an answer of around about 171 seconds. Thank you, the boss has got there, and Evan too, brilliant. And quite correctly, you've shortened it to 3 significant figures, you've rounded it, which is common sense, yeah, to do that, or maybe not, that's a good idea. So 171 seconds, good job. Thanks to CAD-S, brilliant. So next question then, an electric current of 50 amps passes through a speaker for 1 minute. So again, think about SI units and what numbers we're going to have to use in the calculation. calculate the charge that passes through the lamp in that time. So we're going to use the same formula again. We want to find charge. Charge is Q in coulombs, remember, and Q equals IT. So this is a straightforward use of that formula. Current in amps times time in seconds. Q equals IT. So we're just going to do the straightforward calculation here. We've got 50 amps. What are we going to use for time? 1 minute. Thank you, Evan. Yep. Brilliant. Thanks a lot. Yep. So of course, convert a minute to seconds. So we got 50 times 60, which of course, as some of you have already put in the chat, is 3,000. 3,000. So 3,000 coulombs of charge is going to pass through that speaker in a minute. An electrical current of 50 amps. That's one heck of a speaker. Right. Festival speaker, base unit maybe. Right. Moving on from there. How confident are we about using Q equals IT and rearranging it, understanding that Q is the symbol for charge in coulombs and I is the symbol for current in amps, and T for time in seconds. If you could put me a 1 or a 2 or a 3 in the chat, be really grateful just to make sure that we've spent enough time on that. Any more questions in there as well, please feel free. Thank you, the boss. Okay, great. So I'm seeing a lot of ones. That's always good to see. So you seem fairly happy with that so far. So good. So let's have a look at some exam questions. Yeah, I took your 11 as a double one, the boss. So that's all right. Okay, let's look at some exam questions then. So the first one, Q is just charge ultimate. So Q is the letter we use to represent charge, of which the unit is the coulomb, which is capital C. So what is meant by current? We've just been talking about current, so describe what current is. What makes up a current? There we go, Evan's got it. No worries, ultimate. So thanks, Evan. The current is the rate of flow of charge. Good, yeah. It is the rate of flow of charge. You could say the flow of charge, but I'm pretty certain it's right to say, and I would advise you to say the rate of flow of charge, because current is Q over T, it's coulombs per second, so rate of flow of charge. And then the next question there, complete the sentence by putting a cross in the box next to your answer. The current in a filament lamp is a flow of what? So we've got a filament lamp, conventional light bulb, and you've got this bit of wire in there. And there's current going through it, so I'll draw a little cell. Here we go. What's flowing in that filament lamp to make it glow? And the answer, thank you all of you. Yep, C, electrons, yeah. So it's a flow of electrons because we've got a metallic conductor in the filament lamp, or carbon or graphite, and that's what's allowing the electrons to flow within it. Good. Let's have a look at another example. So a torch has a battery and a bulb. The current in the circuit is 0.08 of an amp. Calculate the amount of charge passing through that circuit in 2 minutes. So we've got a current. We want to find charge. We want to find Q. We know I, and we know the time. And it's 2 minutes. So like we did before, obviously, we need to turn that into seconds. So that's going to be 120 seconds there. So I'm underlining the key information in the question as I look at it. I'm thinking about what I've got and what I haven't. And I know that the formula I'm going to use is Q equals IT. I know T, I don't know what Q is. So that's what we're trying to find, the amount of charge. So Q is simply the one times the other. So I times T, it's 0.08 times 120 seconds, which some of you have worked out already, is 9.6 coulombs with a capital C. Yeah, capital C for coulombs. The exam boards can be a bit pedantic later on, especially at A level, actually, if you don't get the capitalization right. But 9.6 coulombs of charge, good. And I think looking at the chat, I think a lot of you have got that and aren't having any problems. Correct me if I'm wrong, go on ultimate. No, 9.6 C is good. Q is just the conventional symbol that we use to represent charge. So Q, the charge in coulombs, is used the symbol Q. It's measured in coulombs. It's similarly odd that I is used for current, and yet we use the actual unit of current is amps. Time is more obvious, and the unit though is seconds, not T's. So Q represents charge. It's just convention, and you'll see Q in all of the equations in any formula and data book as you move on to A level. Okay, so we've tried a few exam questions now. Let's move on to voltage and resistance. So I'll answer one of Lily's questions in a moment because she was asking about which side of a battery or a cell was positive, and I'm going to have an opportunity to show that in a minute. So in order for a current to flow in a circuit, what needs to happen? For the current to flow in a circuit, what do we need to do? What do we need to do to these electrons to get these electrons to move this way? Okay, so the electron flow that's going to the right, what do we need to do? We need a voltage, Dana, thank you, brilliant. So Aisha, there are definitely live sessions for A level. Yep, they're not done by me, they're done by a colleague of mine, Snap Revise, and you can, I'm sure, find some examples on the website or on the YouTube if you have a look. So we need some force to push these electrons around, that's correct. So we need a potential difference, which is a difference in energy between the beginning and the end of a circuit. I'm not going to complicate that any further. I'm just going to say that there must be a source of potential difference. And we quite frequently shorten potential difference to PD. So I wouldn't advise you do it in an exam question, but you might see that written down in some notes. PD, potential difference. Now, potential difference is just a posh way of saying voltage, okay? But the exam boards now require you to use that phrase, potential difference. So whenever you think of voltages and you're measuring them across a component or a battery, think potential difference instead and write down the potential difference across the cell is, rather than the voltage of the cell is, just because then you'll be using good language and getting into good habits. So we need a potential difference. So the potential difference from the battery what's the symbol of the battery's terminal going to be on this side of this piece of wire? The electrons are going to the right. So what is it going to be a plus or a negative terminal that we put on the left-hand side of this wire where I'm drawing the arrows? Is that going to be the plus or the negative that's making those electrons go to the right? So I'm getting a lot of pluses at the moment. Don't let the positive ions of the metal make you think that. Doing the classic teacher thing now by saying I'm getting lots of positives in a way that suggests that's not right. So what's going to push the electrons away from the left-hand side and make them flow to the right? Yeah, you're getting it now. Yeah, thank you. Samana, the boss, brilliant. So yeah, we've got the negative terminal of the battery here. Okay, the negative terminal would need to be connected to the left-hand side of that wire because negative charges will repel each other. Yeah. And then therefore the other side of the wire, in order for these electrons to flow, you need to put the positive terminal of the battery, connect it to the other side of this wire here. And that provides the force that causes the electrons to flow from, I'm going to use a little abbreviation, from negative to positive. My little abbreviations for negative and positive. That's just me being lazy. Do write it in full when you're writing an answer. So that's forcing the electrons away from the negative terminal, ultimate spot on, using the right language, and it's pushing them around towards the positive terminal of the battery. So the potential difference is a power source, okay? The potential difference of a power source is what? So what exactly does potential difference mean? I've mentioned energy. Does anyone know what potential difference really represents? So what's the meaning of that phrase? What is a potential difference? When we move something, we do something on it. And we've covered this in an earlier session. So if you transfer energy into a system and you move something, you have to do something on that object. It's a word that you associate with lots of other things in everyday language. And a potential difference is a measure of this. I'm trying to hint at something, see if anyone gets it. I'll tell you all in a second. Oh, Ultimate's got it. Akansha's got it. Brilliant. Thank you. And Dana. Cool, work done. Work on it. Evan, good. So the potential difference of a power source is a measure of the work done. So it's a measure of the work done to push the charge around the circuit. In this case, that charge is electrons. I'm going to use the word charge because it could be something else. You might have in that circuit a beaker of salt solution. Same would apply. So potential difference is a measure of the work done to push charge around a circuit. Good. I'm going to move on to talking about another property now. And work done per coulomb of charge is spot on us here. We're not going to dwell on that one in this particular session. Okay, so resistance in a circuit. Resistance. Is it futile? Right. Resistance is a measure of what? So Asira is absolutely right, though. PD is work done per coulomb, energy per unit charge. So you often talk about circuits having resistance. What does resistance do when these electrons are being pushed around the circuit by our potential difference? So we have some source of potential difference. We'll label that in our circuit. So there's our potential difference source here. Oops, it should be a D. Turn it into a D. There we go. That says potential difference. And to answer Lily's question from earlier, the positive side of a battery or cell is the long line, and then the little short line is the negative side. Okay. So yeah, it opposes the current. It slows the electrons down. It's a hindrance to flow of charge or electrons. Very well worded, Asir, thank you. Right. So yeah, resistance is a measure of how difficult it is for current to flow through a circuit. Resistance will slow the current down. So I'll just label our resistor here. Yeah, sorry about my handwriting. There's our resistor there in our circuit. Has a resistance R. Not going to worry about that just yet. There we go. So the resistance of the circuit is a measure of how difficult it is for charge to flow through the circuit. So if we put a resistor in a circuit, what are we going to do to the speed of the electrons moving in the circuit? If we have a wire and we add a resistance to that loop of wire, what's going to happen to the speed of the movement of the electrons? Thanks, Dana. It's going to slow it down. Brilliant. So the resistors slow down the speed of the resistance. The electrons. And the boss has said resistors are used to vary the PD. They can be, but their first effect is to reduce the current. Samana, thank you. Slow down the electrons and to, in this case, well, slow them down. So it would make the current smaller. So resistors are used to change the current flow or the current flowing. They'll actually change the amount of amps flowing in parts of a circuit. So if we add a resistance to a circuit, we're going to make it harder for the electrons to flow for a given potential difference. So we're going to make the current smaller, going to decrease the rate of flow of electrons. It's not wrong what the boss said, that resistors can be used to vary potential difference. The potential difference across the resistor is a measure of the difference in energy of the electrons going in one end and out the other. And so you can use multiple resistors to provide different voltages. Yeah. Let's have a look at this simple circuit now. Let's come back to some things we've covered already. So we've got a source of potential difference. In this case, there's a diagram on that circuit representing a cell. And then here we've got a resistor. So can someone tell me, if you think of clockwise and anti-clockwise, which direction are the electrons flowing around this circuit here? So this circuit, which direction are the electrons flowing? Are they going anti-clockwise? I'm going to put that at ACW, or are they going clockwise there, CW? Which direction? You can say ACW or CW if you like in the chat. Where are the electrons going? Anti-clockwise we've got from Akansha, Just looking what other people have written. I'll come back to your question in a moment, Ultimate. Absolutely. Yeah. From the negative to the positive, anti-clockwise, a-clockwise. Yeah, brilliant. Okay, so Tamanna, the electrons are going anti-clockwise because this is the negative side of the battery or the cell. So the electrons are being pushed away from the negative terminal because they have a negative charge. So the electrons are actually flowing this way. Okay, electron going around circuit. Yeah, there we go. And of course, it's a series circuit, so it's going to be the same rate of flow of electrons everywhere in a series circuit. There's our electron flow indicated there. And I tend to always describe the electron flow using an arrow outside the wire. This is currently for foundation and higher floss, where there's higher content only. That is detailed on individual slides, and some sessions are for higher only. So the electron flow is actually the opposite direction to conventional current. When we tell which direction the current flow is in a wire, we tend to draw arrows on the wire itself with a symbol for current, which is I, and conventional current is described as flowing from positive to negative. So these arrows I'm drawing here with an I next to them, they represent the flow of conventional current. And that, I think, is the only truly slightly confusing thing about electricity. Once you remember that, there's not a lot else within the topic apart from the use of formula and your confidence in doing that, rearranging them. That really, I think, should throw you too much. I actually really like electricity as a topic myself, and I find that once it clicks, you find it clicks and you get it all. You just need to practice if you're not feeling confident. There was a question there as to why metals conduct electricity from Ultima earlier. Metals have an ability to give up electrons. And I think it was you or someone else that described a sea of delocalized electrons. So in a wire or in another metallic substance, you've got a lattice of metal ions, which are just vibrating about fixed positions, and they're giving up electrons, and those electrons are able to move. And in just a bit of wire, if you're just holding a piece of wire and it's not in a circuit, those electrons drift around randomly. Let's bash into each other, and that's that. They don't carry any energy in any particular direction. But as soon as we put a potential difference across our wire from one end to another, then we provide the force that's needed, the EMF or electromotive force, from the potential difference of the battery to make those electrons begin to drift in a certain direction. And that's always from the direction away from the negative terminal of our potential difference source towards the positive terminal. I hope that answers your question, Ultimate. And coming back to where we are now. So conventional current, thanks Dana, flows from positive to negative, but the electrons are really going the opposite way. Okay. I'm going to move on from that slide and just check on my time. Good. Okay, so let's have a look at a question. So potential difference. Potential difference, we use the unit of volts, don't we, for potential difference, and we can describe it as equaling something times something else. Can anyone remember what potential difference is? Can we define PD? So what actually is potential difference if we want to calculate it? Evan's got there, thank you. Yeah, the actual definition is joules per coulomb, that's right, Dana. And so it's current, in terms of calculation, rather, we can use Ohm's law. It's current times resistance, so it's current in amps times resistance. Resistance has a sensible symbol R, and we measure it in ohms, which is the omega symbol there. Okay, current in amps. So V equals I times R, and the unit of R is ohms, which is spelled like that, OHMS. Okay, so V equals IR, that is Ohm's law, basically. Not going to go any further on that one, that's for a later session, but V equals IR. So if we've got a circuit consisting of a 12-volt battery, can you underline my key facts again? It's got a resistor in it, it doesn't say what that resistance is, and it's got a current of 4 amps, calculate the resistance. So we know the V equals I times R, V equals IR. So the symbol for PD, thank you for that, is volts, capital V. good question, Floss. Thanks, I didn't mention that. So V equals IR, R is measured in ohms, current is measured in amps, but V is measured in volts. So you would literally write it V like that. Okay, so we need to find a resistance here. We need to rearrange that formula. What is resistance going to be equal to? Can you tell me? What's the formula we need to use? Some people jump ahead to the answer, that's fine. Just want to make sure that everyone can do the rearrangement. So R equals V over I, Dana, thank you. So R equals V divided by I. We would divide both sides of that formula on the left here by I. And that's going to be 12 divided by 4, which you've already got there, is 3 ohms. There we go. And there's my rather dodgy ohm symbol. But there we go, 3 ohms. That's the resistance. And quite a few of you put that answer in the chat already. Good. A few more examples. Calculate the current flowing through a lamp if its resistance is 3 kiloohms and the PD across it is 12. So we start with our formula V equals IR again, start with Ohm's law. We want to find the current. So what's current going to be equal to? I equals, what do I need to write next? So we're finding current, we're rearranging V equals IR, so that I equals what? So not the answer, just the equation rearrangement. V over R, good, V over R, Dana, thank you. So I equals V over R. So that's going to equal 12 divided by 3,000, not 3. Okay, divided by 3,000 because there's the k ohms. So I see one or two of you have put 4 there in the chat. If you were to do that in an exam, you'd probably get some marks because you've clearly done something of the calculation and the formula rearrangement correctly. But by getting the power of 10 error there, you'd lose a mark. So the answer is in fact, yeah, 1,000th of 4. So 0.004. We can write that as 4 milliamps. Okay, the milli stands for times 10 to the minus 3. So we can write it as 4 milliamps, or we can write it as 0.004 amps. Just be careful to see whether the paper you're doing requires you to answer in milliamps or amps. Okay, it's 0.004, Jose. I hope I'm pronouncing your name right. So 0.004. 4 times 10 to the minus 3 is another way of writing it. If you really want to be scientific, 4 times 10 to the minus 3 amps if you want. Thank you, Ultimate. Okay, so next question. 5 milliamp current flowing through a 15 ohm wire. So we've got a wire with a 15 ohm resistance. So R is equal to 15 ohms. I'm just going to write that fact down because the way it's stated in the question is a bit odd. We've got current there of 5 milliamps. Let's put that down here as well. So I equals 5 milliamps. What does the milli mean? Ultimate knows the answer. If I was going to write that I down again, 5 milliamps, it's 5 times 10 to the minus 3, so it's 0.005 amps. Okay, no, the little m means divide by 1,000. Well, like a little k means multiply by 1,000. Okay, so that current is 0.005, and we need to find the V, the potential difference. So V equals IR. We've had a look at what R is from the question. We've had a look at what current is. So that's going to be 0.005 times 15, 0.005 times 15. And the answer's already been put up there by Floss and the boss, is 0.075. Yep, 0.075 volts. Volts being the unit for potential difference. Okay. So again, just once you get used to using these equations, it's just looking at the facts, looking at the questions and seeing what's missing, seeing what you asked for, plugging in the numbers. So can I have another look at having a look at how confident you're feeling about all of this? Thank you, Ultimate. So 1s, 2s or 3s, please, in the chat. If you're happy, 1s, please feel, I know it's sometimes hard if you're not quite happy to put a 2 or a 3, because obviously I do want to go back then and I've got to ask you what you'd like me to cover again. So, but don't be embarrassed about it, it's fine. Is there anything that any of you would like me to just recap? So I can see a few 2s and 3s. So particularly those people, if you want to just put in a topic, what is there that you'd like me to cover again, or any particular questions? Conventional current. I knew that. I'm very pleased that question didn't come up earlier, but it's come up now, and I think that's fair enough. Okay. We do have a drop-in session next. Yes, true, Evan. And I will be finishing this session just a little bit early so I can prep for that because I need to start a different stream. But conventional current is the flow of current described in a circuit as going, sorry about that terrible drawing there. Conventional current is the direction of current flow in a circuit, and it's considered to go from positive to negative. So conventional current is positive to negative flow. Well, that's the direction of current. Now, the confusing thing about that is that the electrons actually go the other way. So in order to carry that energy, the flow of electrons giving rise to that current flows from negative to positive. And I know that is a little bit, it makes you ask why. I believe, and you can look it up yourself, I believe it's down to historical understandings of what was actually causing a current in a conductor. I believe it's down to the fact that originally scientists thought that current carrying particles were positively charged. But do your own research on that. I don't think I'm wrong, but it might be. But conventional current is certainly the direction of current. If you were asked to draw it on a circuit, always in the direction from positive to negative. The free trial code, I would use it soon. We start the sessions next week. That would require a subscription. So if you want to continue where you left off, then you could use it sometime this week. I'm sure my colleague in the chat there will be able to clarify any other questions there. Okay, I am teaching the drop-in session next. And so, yeah, there'll be a 5-minute break after this one. I'm going to finish a little bit early and then I'll be back in the drop-in. Okay, are there 5-mark calculation questions on electricity? There could well be, Tamana. I can't say for sure, but there could well be. There's no reason why not. Let's have a look at another question here. So Susan is investigating electrical circuits and she wants to research voltage. What's another name for voltage? Let's have that quickly in the chat. I'm hurrying you along a little bit now. Sorry, I shouldn't do that. It's just I want to get, I've got 5 minutes. So potential difference, brilliant. Thank you. And that really is the phrase you want to be using when you're describing voltage. Voltage, the word will come up and you measure voltage in volts, but you measure potential difference in volts. That's what we want to use. Complete the following sentences about voltage using words from the list. So the voltage is a measure of the push given to charges in a circuit by what word? There's only one word that fits. What of those things is going to give a push to charge? The boss, Tamana, Evan, thank you. The battery, in this case, is going to be a battery because there's no cell in the list of words. So battery is the only option there. Second one, the voltage between 2 points depends on the work done on what as it moves between the 2 points. So if you measure the voltage across a resistor in a circuit, you're measuring something between those 2 points. The work done on what? What's having work done to it in a current flow? Think about the words. What's moving here? Is the wire moving? Is the wire having work done on it? Is it moving anywhere? It's not moving anywhere. Thank you, Evan. Yeah, brilliant. Evan's right. It's the charge, okay? It's the electrons, Mark, more precisely, absolutely. But the word that's available is charge, okay? So the voltage between 2 points depends on the work done on a charge as it, and there's another clue there in the question because it's a singular, yeah? As it moves between the 2 points. So work done on the charge. So the charge is the total number of coulombs passing between 1 point and another in a given time in 1 second. That will give you the current in amps. So work done on the charge is a measure of is what you're going to get when you measure the voltage. Okay, we've done a lot of practice questions. I'm a little bit aware of that, and I do need to just wind this up over the next 5 minutes. Please don't rush off because if I can have time to do it, I want to just show you the Snap Revise tutor site. The work done. Okay, well. Potential difference is work done per unit charge. So the formula for work done in electrical work done is going to be work done is equal to VQ. It's going to be potential difference times charge. Okay. Let's finish off the topic though. I'm hoping you can define what charge is in terms of coulombs and what current is, and you can recall the equation Q equals IT, and understand how current can happen in a conductor like a metal, which Ultima asked for more information on, which is good as well. Understand that potential difference is required for a current to flow, so you need some source of energy to do work on the charge in a circuit, and use the relation between current, potential difference, and resistance. So use V equals IR. Certainly, see you in a moment, Ultima. Thank you. So I'm hoping that's the case. Are there any questions? There's a petulant pigeon there flapping its wings. If anyone's in a flap about any of this, please ask me. I do have just a tiny bit more time, a couple of minutes, and just about enough time probably to share with you the tuition site so you know what to look for when you go to Snap Revise site. Any questions? I'm not seeing anyone popping any up at the moment. So what Snap Revise are offering, thank you, Khadija, is 3 classes or more a week. The full curriculum that you are covering will be covered by Snap Revise. Very good quality handouts, access to all of our past recordings, and also one-to-one support in the drop-in sessions. In the drop-in session, Tamana, we are going to be going through some exam questions which are based on feedback from students over the past weeks as to what they'd like to see done a little bit more. So Daniel, head on over to the website if you'd like to know a bit more about the costs. I'm just going to stop sharing this screen, and if I can find my website, which is there, I'm just going to share something else with you. Which hopefully will come up in a moment. Excuse me for the quiet little lull there. Right, okay. So this is the Snap Revise website. If you head on over there to snaprevise.co.uk, and if you click on tutoring, then tutoring will take you to this page, and it will tell you what subjects are available, online tutoring, and you've got A-levels, obviously there you've got GCSE chemistry, biology, physics, and maths. By the way, the maths session today that was due to take place at 6 p.m, I'm afraid won't take place today. And if you click on the tutoring topic of GCSE physics, in this case, there is information about what is going on, how much it costs, and there is the answer to some of your questions. It's £49 a month, but you'll also see a calculation of what that would cost you if you were being seen by a private tutor, and it's going to be an awful lot more. For the number of sessions you get, works out about £3 a session. Having been and am a private tutor as well, this will represent much better value for you to actually just be paying £3 a session rather than so much. Okay, I will leave you at that point and see some of you in the drop-in session next, but thank you very much, and I hope that has been of help, and I will catch you on Thursday for the next physics. Okay, take care, folks.